I am going to talk about machine learning, and during this presentation I will try to explain what is really machine learning, what are different learning types, possible use cases, and then on small live coding example I will present Apache Spark, and at the end I will leave some thoughts how this processing could be improved to get better results, and also how you can learn more about Spark. But let's start with quotation. Do machines think? It's a question asked by Alan Turing in his scientific paper in 1950. In scientific paper in which he asks, which he studies different challenges which stands before process of learning machines. And this paper is also a source of so-called Turing tests in which we have some independent judge or interrogator who talks with different people and tries to guess who is really a human and who is a machine. And until today, no machine has passed this test yet. So what is really machine learning? In machine learning, we try to make machines think like us humans, to be able to detect some patterns in data, to be able to predict basing on that data. And they can cope quite well currently with some scenarios when they have large amounts of data with defined algorithm, etc. But they still need us humans to define the way of processing, process of data preparation, algorithm, which would be optimal for it. So they won't rather take over the world today or tomorrow, but we'll see what will happen next. And there are a few types of learning. First of all, there is supervised learning. And in supervised learning, we are able to verify if this learning is correct. So there's some type of supervision. In supervised learning, there is always some output variable. And this output variable can have different types. So in classification, this output variable is some type of nominal categorical value. For example, email classification to two categories, spam and not spam. And then there is regression. And in regression, this output variable is number. So this can be predicting stock prices. Then there's second group in unsupervised learning. But in unsupervised learning, there is no such clear output variable. And we are more interested in what is really the whole process, what is the result of this learning process. In clustering case, we just group objects which are similar together. But there can be different measurements of similarity. We can group events which have similar location, but we can also group people who have some similar interests in social network. And then we are able to aim some marketing campaign to a very specific group of people. And we are more interested in what groups will be created during this learning process, who is in which group, and what it really represents. And second subtype of unsupervised learning is the dimensionality reduction. And in this problem, we just want to reduce number of attributes. So we can imagine that we've got some examples put in three-dimensional coordinate system, but they are can be clearly split in 3D, but it may be still possible to map them to 2 dimensions and still to be able them to split to 2 groups. So this 1 dimension is not really needed. So by manipulation, it's possible to reduce the number. Then there is a group of semi-supervised learning. And in semi-supervised learning, the majority of our examples does not have any labels. But there is a small subgroup with labels. And we can say here, for example, that labels are expensive to get or are hard to get. But having them only for that small group can still improve results in this category of problems. And the last group is reinforcement learning. And this group can be the easiest to explain by example of artificial intelligence in games. So in games, we've got some initial state, there is some goal, and there is possible state of moves. And when the artificial intelligence chooses the right moves, which moves it forward to the goal, or reaches this goal, gets some bonus points, some rewards. And when it does moves which are not really expected, where it dies, for example, then it gets some minus points. So it tries to maximize the number of points it has. And this can be also applied, for example, to movement of robots. When we want to move some robot from point A to B, and if it reaches the goal, it gets some bonus points. But if it will stuck to the wall or hit some obstacle, then it will get a negative reward. I have mentioned here AlphaGo. It's algorithm from Google for the Go game. And it's worth to notice that Go is much more complicated game for computers than chess. And quite lately, it was able to finally beat human Go master. So it's a recent development. And there are also different use cases. There is voice recognition. And in voice recognition, we might want to recognize specific words or sentences, but we also can recognize gender or recognize voice of a specific person. And in this group, we have all these assistants like Siri, Cortana, etc. Then fraud analysis. For example, in Poland, there was idea from the government to gather all possible invoices from the country to one large system, and then run some big data algorithms to classify them to fraud and not fraud. Face detection related also to image analysis, ads on websites. And when we're having some ads on websites, usually the company who shows these ads gets money only when this ads gets clicked by the viewer. And so this company who shows these ads wants to maximize the probability of clicking by displaying the right ad for the right person. So it's a matter of detecting the profile of the viewer and matching the profile of the ad with the profile of the viewer. So it's also a machine learning problem. Spam detection I have mentioned earlier for the emails. Shop recommendations. So all these recommendations you might get from, for example, Amazon, that you might be interested in this group of products, or recommendations like people who buys products A and B usually also buys product C. So it's basket analysis. Photos description. There are algorithms also from Google to generate caption for pictures. So it is automatically possible to describe when there is some, for example, car standing on the street near tree, etc. Self-driving cars related to a lot of sensors. There is image analysis with detecting cars, pedestrians, recognizing some street signs, etc. And healthcare, having a lot of data about different patients, it's possible to predict what is the best treatment for given patient, what would be the best for him. And there is some standard learning process, and here I am focusing mainly on classification because the example will be a classification-based problem. But generally, this learning process is similar for different types. There are some similar elements. So first of all, you have to gather your data. And you can have data put in different sources. So you have to gather this data from different sources. They can be in different formats. So you have to bring them to a common format. Then, if you have some categorical values, you have to standardize the names. There can be different names in different databases. And once you have done that, you have to clean that data. There can be some values missing. If value is missing, you have to decide, do you want to remove such example, or for example, to approximate value. It can be some median, can be average or something else. But apart from missing examples, we have some outliers. And outliers are examples in which we know that value is for sure wrong. This can be a case where there is some value which usually has values between 0 and 10, And here we see, for example, 10,000. So we know it's for sure wrong. And again, we have to decide, do you want to remove it or to put there some median or something else? After cleaning, you might want to do feature engineering. It's generally a process of adding some additional features. So, for example, you may have some name field in which would be the name and surname and some title. And the feature engineering process would split this field to have, for example, this person title in a separate field. It could be used for some problems. But also for voice recognition. You won't just put all the bytes to your data, because for different problems, for voice recognition, for sentences recognitions are valuable other characteristics than, for example, for gender recognition. And once your data is prepared, and it then can take some time, some people even describe that the data preparation process takes 80% of time, then you split your data. You split data to two data sets, to train set and test set. And this can be, for example, 3/4 and 1/4 of the size. And you take only this train set and you perform the learning process. So you use some machine learning algorithm which knows only here this train part, and it produces some model. And model can have different representations depending on the algorithm. It can be some set of rules, this can be some decision tree, this can be a set of parameters for some neural network, depends. And once you have this model, you want to evaluate it, to check how good it handles new data. So you apply this test set it doesn't know to that model and perform evaluation. And in evaluation, for example, you might want to check how many of the examples are correctly classified. So you can get some percentage accuracy. And when you have this accuracy, you have to decide if you are satisfied with it and go to next steps. Or if you are not, you must go back, add other features, change algorithm, change some parameters, etc. And finally, when you reach your optimal model, you can take new observations which doesn't have the label and predict the correct label. Example. So I will use today Apache Spark. It was today described also on some other sessions. But generally, Apache Spark is a big data tool. So usually you would use it for scenarios where we can't analyze our data on single node, when node can be scaled more vertically, where we're lacking some computational power or really lacking memory, for example. So Spark is usually run on clusters. And in Spark, you usually operate on RDDs, which are like distributed collections, or you operate on some higher level APIs like data frames, but beneath them there are still RDDs. And RDDs are like distributed collections, so you apply on them some transformations, and these transformations occurs on specific nodes where that data are located. And it's quite clever because when some node fails, it doesn't need to restart the whole computation, but it only can restart the computation on this very specific part of data which was analyzed on a given node. And Spark has some extensions. There is support for SQL language for querying multiple data sources. MLib, we will focus on this today. It's a machine learning library. GraphX for graph analysis, Spark streaming with stream processing, and it offers APIs in different languages. So there is a Scala, Java, Python, and R, but with some limitations. And we're going to analyze today a very simple problem. We want to classify conference talk abstracts into tracks. So on different conferences, like on this today, there are tracks like big data, mobile, backend, methodologies, etc. So I have gathered abstracts from a few conferences. There are over 100 of them. And I have put them in a single CSV file, which contains generally the name of the track, which I have standardized among all these conferences, title of the title of the talk, and abstract of the talk. Okay, and now we can go to the code. And generally, I'm running here a Zeppelin notebook. It's one of the possible notebooks. You might have heard about, for example, IPython or Jupyter. And generally, notebooks are like web applications which can connect to Spark and other systems, in which you can execute some code, you can execute Bash, but you can also write some comments, for example, in Markdown. So you can write the whole process of data analysis, leaving some comments, why do you use some method, etc. And here I'm running a single Spark instance together with Zeppelin in a Docker container. And in first step, I'm just executing Bash to download those abstracts from my GitHub repository to this Docker instance, and there are some imports. And now, so we have to load that data to a data frame. So Spark is a Spark 2.0 and 2.1 entry point. In previous versions, you might have encountered, for example, Spark context. So we say that you want to read with some options. And I define here two options. First of all, my CSV file has header, which contains column names. And second option is I will move to this to new line, delimiter, which is specific in this CSV. And I say that I want to read a CSV file named abstracts CSV. And let's see what's in that data. z.show, it's a function from Zeppelin, which displays data in form of table. So maybe a bit slower, a bit lower font. Okay. There's table, there's label. In first example, there's label backend with some title reactive streams principles applied in Anaka streams, and there is text of the abstract. And that's all. And you can also display this data in different formats. So for example, here you can see the distribution of different labels. So there are 22 abstracts on big data, 21 on backend. There's DevOps, frontend, Java language, methodology architecture, mobile embedded, and 8 in programming languages. And now, I have not said that before, but most of the machine learning algorithms require to have numerical input. So both your label and set of features needs to be numbers. So we have to transform this data set from strings to numbers. And I will now apply a few transformations to show you how to do this. So let's start with the label. So we want to transform this string label to number. And to do that, we can use transformations from Spark called Spring Indexer. And we have to define two things. What is the input column for this transformation? So there is column named label currently in our data set. And what is the output column, which will be indexed label. And I have to provide here our data. And now I will step by step apply all these transformations to show you how this data changes, how new columns appear. But at the end, we're going to create single pipeline combining all these transformations to one processing pipeline. So value indexed equals string indexer transform data. And let's display it. So there's again our table, and there is new column named indexed label. And so we see here that for a label named backend, we got value 2.0, and later, for example, we here see value 1.0 from label big data. So our label transformation is ready, But at the end of the process, we'll need to do a posit transformation to transform back from the numerical representation to string representation. And let's define already this transformation. So this is index to string. And we have to define again what is the input column. And this will be prediction. And what is the output column? And let's name it prediction label. And we have to provide here what is possible set of labels from the string indexer labels. And now we have to transform our features. So we've got the title and abstract. And if you would read this whole data set, it often appears that title is very important. Often title contains, for example, technology name, which is later never included in the abstract. So let's just concatenate this title and abstract to one text, and also to show some Spark features. And to do that, we'll use SQL transformer. And it's a transformer where we can define SQL statement. So we say that we select all existing columns in our data set, plus we want to concatenate title and text as new column, title and text, from this. And this means that from current data set which is transformed by this transformation. And let's apply it and see what it produces. So value transformed equals SQL transformer transform indexed. And let's display it. Okay. There is some issue with Zeppelin in current version that sometimes with this zoom it does not display this table. So sometimes I have to refresh this notebook. Generally, this notebook saves all the answers, so even if you close this notebook and reopen it, then all these results we see now are still saved there. So there is label, title, text, indexed label, and there is a new column, title and text we've just concatenated. And now we'd like to split these texts to separate words, because we need an array of features. And to do that, we'll use regex tokenizer. It's another Spark transformation. Where again, we have to define what is the input column. So here it was title and text. And what is the output column. And this will be words, because this will be separate words. And we have additionally to define what is the pattern. So here the pattern would be to split this on every non-word character. And let's see what it creates. So there is regex tokenizer transform our previous data set, which was called transformed. And let's display it. Again, it didn't display the table, so quick refresh. And we see there is a table, title and text, and there is new column words with just arrays. And now when we look at all these words, there are some words which are not really needed in our learning process, because there are some stop words like in, we, to, etc. And they are not really too valuable. So let's remove them. And this can be also done quite automatically. There is a transformation named stop words remover. And with this transformation, we again have to define what is the input column. And here this is column words, and the output column, which we'll name filtered. Generally, we can configure this stop word to provide our own set of stop words we would like to remove. So our new dataset filtered equals stop words remover transform words, and let's display it. So there is a table, there was title and text, there were words, and now there is a column filtered. And once we look at it, these all stop words are removed. For example, there was reactive stream principles applied in akka streams, and now there is no that in. So generally these arrays are smaller. And we have now array of words, but now we have to transform it somehow to numbers. And there are a few possibilities. So we could imagine such scenario in which we would have the whole English language dictionary, and we would create some large vector with thousands of positions. And in this vector, on specific one position would correspond to one word from dictionary. And we would mark zeros when the word does not occur, and we would mark one or number of occurrences of given word. But first of all, this whole dictionary can be large. And additionally, in case of abstracts, technology names are not only English language words, so it wouldn't really work for us. And we would use a small trick. It's called hashing trick. And to do that, there's already transformation called hashing TF. It's a hashing term frequency. And we define here the input column, which is filtered, right? And we define what is the output column, which will be already features. And we have to define additional one parameter called number of features, example 2048. And this means that it gets each of these words, it calculates hash of this word, then divides modulo 2048. So it's like putting these words hashed to one of 2048 buckets. And it just stores the number of occurrences. So there can be some conflicts. It's possible for multiple hashes to fit to the same bucket, but let's not worry about it now. And generally, it's possible to tune this number of buckets. So let's see what it really produces for this dataset. So hashing term frequency, transform, filtered, and z.show features. So we have here table. We had title, text, words, and now there's new column called features. And really expected here to see vector with 2048 positions, but Spark is quite clever, and it knows it's a sparse vector. Sparse vector is a vector in which there are a lot of zeros. So it is really interested in what numbers are filled. So it consists of three values here. First, 2048 is a size, and there are two arrays. And one array is an array of positions, and second is an array of numbers of values. So for first example, we see here number 39. So this means that from position 0 to position 38, we have only zeros. Then at position 39, we have value 1. And then between 39 and 148, again, are only zeros. And at 148, it was, I think, yes, and 148, there's again 1, etc. So just indexes and values. So this saves a lot of memory for in this case. And we have now both a numerical representation of label, and we have numerical vector of features. So we can already apply some machine learning algorithm. So we'll use here naive Bayes algorithm. Generally, this algorithm calculates probabilities of occurrences of specific words in specific category. And it's called naive because it naively assumes that these probabilities are independent. And we have defined for him two parameters. So there is label column, so this is indexed label. And what is the features column, which is features. I won't apply it now. Let's already define our whole pipeline of processing to show how this all works together. So we've got pipeline. And we set here stages. So what we do in the order. So first we had our data, and we have transferred our label to numerical representation using string indexer. Then we have concatenate title and text using SQL transformer. Then we have split our title and text to separate words using regex tokenizer. Then we have filtered these words, removing the stop words. And then you have hashed using hashing term frequency. And this is the place for naive Bayes. And naive Bayes produces the numerical prediction, and we want to transform this numerical prediction back to the label. So it's index to string. The one transformation which we have defined at the beginning, but we have not used. And we will create now the model, but we will actually create this model using the split to train and test data sets. So let's split our original data. So we had the data, and we perform a random split. And we perform the split to 3/4 and to 1/4. And to create a model, we take this pipeline and represent to it the train data. And now we won't see too much, so let's already check what will this model do with our data sets. So what it would predict. So train predictions equals model transform train data, and test predictions equals model transform test data. And let's display the test predictions. There is some misspelling, index to string. Okay, it worked, but it didn't display the table, so quick refresh. And there's different first row, of course, because we have split the data to two data sets and randomly we have randomly split. So this is our test data set and what it contains. So in test data set, for example, we have advanced Spring Data REST with label backend, and we have applied this pipeline to this data set. So we have all these columns which were creating manually. So there's indexed label, title and text, words, filtered words, features, and something new. There are raw predictions, which are one of the results of naive Bayes, and probabilities. And now there's numerical prediction of this algorithm, and the prediction label, it's transformed opposite side. So we had here Spring Data REST from label backend, as we can see here, and it has predicted backend, as we don't see here. Yeah, okay. There is backend. But to specify what is the full accuracy, how many percent were correctly classified, we won't count it manually. We will use some built-in mechanism to calculate the accuracy. So let's define evaluator, and it's multi-class because we have multiple possible labels. Classification evaluator. Okay, and we have to define what is the label column, so it knows what it needs to compare. So there is indexed label, this column which had numerical representation, and what is the prediction column, which is prediction. And what metric we are interested in. And once we have this evaluator, we can calculate the accuracy and have it by train accuracy equals evaluator evaluate. So we provide the whole predictions. And test predictions. Set prediction column and set metric name. Okay, and it displays two numbers. There's train accuracy 1.0. So this means that this model is able to correctly classify 100% of the trained data set. However, we could be worried here that it's overfitted to that data set, that it's not really reliable. So we have here also test accuracy. So in this try, we got 66% of correctness of the classification. And not bad for first try, it could be improved. But now let's show one additional thing, how to quickly classify new examples which does not have label using that model. So let's define some new observations. So we define new data frame, and we define here some examples. So for example, machine learning by example, and I will present Spark, etc. And some other one, for example, Docker in Java, let's say. Okay. We have examples, we have to define what are the column names. So this was title and text. And now, model transform, new observations. So we are just passing a data frame to it, and let's display it already. So z.show, and there's table. So machine learning by example with text, I will present Spark. So it's generated all these columns we are looking at, and there's prediction 1.0. So it has classified the stock to big data. So it worked quite well. And second one was Docker in Java, and it classified it to DevOps. So it also worked quite well. So now let's go back to slides. So what could be improved to get better results? First of all, our data set could be bigger. Because here I had only about 130 abstracts, so it's too small data set to bring it to production, for example. Then I was tokenizing, I was splitting these texts to separate words just by non-word characters, so for example by spaces. But by this I have lost some info. Because, for example, big data was split to separate words, so we have lost some information. Also, Java EE also gets split to separate words, to Java and EE. So we could have smarter tokenizer, for example, to include such n-grams of words. Additionally, stemming and lemmatization. In English it's not bad, but for example in Polish we have a lot of flexible forms. So simple word like number 2, in Polish it's dwa, have 17 flexible forms. Yeah. And with what you have done today, it would treat all these 17 forms as totally different words. But we know it's the same word. So there is a stemming and lemmatization. And stemming, for example, Porter stemmer, it's some kind of heuristic. It just leaves the common beginning of all these words and cuts off the different endings. So it creates some form which might not really sound like original word, but it might work. It's quite simple. And lemmatization is more advanced processing. It includes grammatical rules of specific languages, and it can be even possible to bring really the word to base form. Next, we have used here hashing TF. So TF is term frequency. So we have included the number of occurrences of given words. So it made important words which occurred a lot of times in given examples. But inverse document frequency additionally lowers the meaning of these words which occurs in a lot of documents. So if something occurs in all documents and wasn't removed by our stop words remover, it's probably some other common word from the given language and rather won't be useful in later learning. K-fold cross-validation. So here I was just splitting data to train and test randomly to 3/4 and 1/4. But there are also other methods, more reliable. In K-fold cross-validation, we split data to K-folds, for example, to 4 folds. And we perform the learning process 4 times. So every time, each fold is in test set. So we take first fold, put it in test set, rest of data is in train. We perform some accuracy, and then we do the same for second, third, and fourth fold, and we calculate some average accuracy. And advantage of this is that this way every example is once in test set, so it can be evaluated. And there is parameter tuning grid search. Spark offers built-in support for that. We had here one parameter which we could tune. For example, this was this number of buckets, number of features. We had 2048. But we can pass to Spark an array, for example, 1024, 2048, some 10,000s, etc. And it will produce models and calculate accuracies for all these parameters combinations. And it will, in output, it will put the model which is optimal with optimal set of parameters. Some links. First of all, there is link to that Turing paper I have mentioned in the beginning. Then link to Apache Spark. Third link is a Databricks website. Generally, Databricks is a company who offers also support to Spark and offers some commercial distributions, but they also have some online cloud in which they run Spark, and it is possible to create some community account, free account in which you can spawn some single node 6 GB memory instance and play with it with built-in notebook. So you have just to create an account. Then there is article from Google about producing captions to images. Kaggle.com, it's a website recently acquired by Google, in which there are machine learning competitions. So there are private companies who often post there are some problems, even giving money for best solutions to solve some big machine learning problems related, for example, to classifying fish by images. There was recently such one. Or there is now competition from Google to automatically categorize YouTube videos. Next, this is the Docker container I was running today with Spark and Zeppelin. So it's just two commands to run this combination. And Databricks Spark Core NLP. It's integration between Spark and the Core NLP library. Core NLP is library from Stanford for natural language processing, and it offers such features like stemming and lemmatization, etc. And last link is the course from the Coursera with Spark and Scala. So it was started, I think, a few days ago. It started this week, so you can still join and learn Scala and Spark. These slides are already available on Software News SlideShare. In slides, there is also link to GitHub repository with this whole data set and this whole code from notebook I was running today. So it's possible just to import this whole notebook file to your instance. And I encourage you also to read our companion blog, where we also blog on some big data topics.